So the way I'm going to go through this is I'm going to do sort of conceptual review, and I've organized some problems from the last few semesters of exams. Um, so yeah, we're going to do like sort of conceptual overall review. Hopefully, the review of the equations and the organization of the equations, sort of as we came across them throughout the semester so far, will help if there's still any question about what to put on the formula sheet specifically. Um, so yeah, so to start, we're just going to start off with this chart that I always go back to. And on this chart, we have sort of our four fundamental concepts that we've encountered so far. So that's force, field, uh, potential, and potential energy. Write them all the way out. Potential and potential energy. And as we've gone through the semester, we sort of filled in each of these with the equations. And this is generally for point charges. So I'm just going to sort of put that up here in the corner, that we are kind of explicitly here talking about point charges, but we build kind of the rest of our physics off of the point charge formulation. So that's why we actually kind of start with point charges and then go from there. So just to recap our equations, hopefully we're all familiar with these by now. We have our electric force, which is K big Q little q over r squared. And just to be consistent, since I put a force arrow on top of my force there, I should put a little r hat here just to tell me that the direction of this force is radial. And that's just what tells you that it's either attraction toward or repulsion from. And then for field, field is pretty similar. But to get from force to field, we divide out little q. So we have k big Q over r squared r hat. And doing that operation that I just said, dividing up by little q, gives us our first sort of bridge from one to the other. And this is an equation that we've used throughout the semester, that the force is equal to the charge times the electric field. So this has been a handy one for when you have a proton placed in an electric field, and we want to accelerate that proton or something like that. In that case, you need to know the force and set the force equal to ma, and so we need to just take the charge and multiply by the electric field. Cool. The bottom half of this, one other thing that I did want to mention is that both of these formulas are vectors, and that means that we need to pay attention to their directions. This seemed to be, at least early on in the semester, I think the thing that was giving people the most trouble was in minding the directions of the force in the field. And so we're going to do some of those problems first. But before we jump into those, let's talk about potential energy and potential. Potential energy comes from the force. It is a scalar reformulation of the force. It comes from integrating the force, the opposite of the force with respect to distance. So you get K big Q little q over r. And then the potential is related to the potential energy. We get V is equal to K big Q over R. Okay, we have some ways that we like to move around. One thing that I want to mention is for the potential energy, we have a rule here that we have one potential energy term. We have one KQQ over R for each pair of particles in a charge arrangement problem. And we talk about in navigating from first thing I want to mention is that in navigating from force to field, we have the force is equal to Q times E. You also could have a similar relationship between potential energy and potential, and this is one that you've probably come across as you've been studying for this exam, and that's that the change in the potential energy of a particle is equal to the charge of that particle times the change in the potential. And we'll talk about how to use this toward the end of the review, but just to give a real quick 10-second definition, if you know the potential in two different points and you know the charge of a particle that you're moving between those points, you can find the change in the potential energy or the work or whatever. Okay, the last bridge that we've spent some time studying and that we will go over today is between field and potential, and how we navigate from field, which is a vector, to potential, which is a scalar. And in that case, we have a sort of two definitions that allow us to go either down or up. The first one is that the potential difference, delta V, is equal to the opposite integral of E dotted with ds, where ds is a differential length, it's a path length, and specifically, generally the way that we use this, of course, is we just do, like, say, the x component of the field integrated with respect to dx, or the y component of the field integrated with respect to dy. And there's also an inverse of this, which I'm going to try to give a kind of clean definition for, and that's that the electric field is equal to the negative derivative of the potential with respect to some direction. So what I'll do here is just give one of them, which is just the x direction, but keep in mind that we could also do the y or the z. And there's a more mature way to write that definition, but I think for the sake of everyone's sort of comprehension, that is enough of a definition just for our sort of one-page review here. Okay, so as promised, I do want to start off with vectors. I want to spend a little more time with vectors, with the forces in the fields and the point particles, because that seems to be the stuff that was giving people the most trouble. It seems like the last few quizzes, actually, everyone's been in pretty decent shape. Even people who were getting them wrong at least sort of knew what they were doing, but it seemed like there were some people who were just kind of fighting for their lives in the forces and fields chapter. So let's go ahead and jump into some exam problems. First one I wanted to look at was fall 2021. And I have a couple problems from fall 2021 that I wanted to look at. But I can't show the problems here because I don't want to get copyright DMCA takedown notice. But we're going to start with problem number 2 on fall 2021. So I'll try to put F or S. Most of the problems that we're going to look at today are either going to be on fall or spring of 2021. So I'll just try and note which exam as we're going. So fall problem 2, we have two identical charges placed in the xy plane and at certain coordinates, and we're asked to find the magnitude of the electric field at some other point. Okay, so our coordinates are 0, 3, and 0, -3. Those are both on the y-axis. So if I were to set up the xy axis, I could say that I have one here and one here, and that these distances are each 3, because one's at +3 and one's at -3. And then we're asked just to find the electric field at a point 4, 0 out on the x-axis. So that will just be, maybe I should extend my x-axis here for the scaling. That'll be at some point out here at a point P, and this is a distance 4. Okay, so I start here, and I know I have identical particles. They both have 2 microcoulomb charges. That's fine. I'm starting to look at the distances, and I'm starting to consider my symmetries and things like that. So first thing that I noticed is that I have 3, 4, 5 triangles in both these cases. If you don't notice that, it's fine. But that's the first thing that I noticed. I know the actual distances that I'm going to want to use are going to be the distances from the particles to the actual point P. And so in both cases, that distance is going to be 5 type. Great. So I know I'm going to have to consider direction because I'm asked here to find the electric field at that point P. And I know that my electric field equation is that it's KQ on R squared. I also know that the electric field is a vector, so I am going to need to consider direction. And I would just go ahead and sort of sketch out my direction. It's going to point away from each of these particles because they're both positive. So that would be down and to the right and up and to the right for the up and down, the higher and lower particles respectively. And so now I start to consider, okay, what component is going to cancel here? Can I say just from my graphic interpretation that one of these components is going to cancel? Well, the particles are both the same distance, 5, from the point P, and they're going to give us the same angle because they're both on a 3 by 4 triangle there. So they're the same distance, and they're going to make thus sort of the same angle here. And we also know the same magnitude. So that's all of our conditions. Remember, the conditions that we need in order to cancel out a given component is we need to have the same charge, we need to have the same distance, we have both of those, and then we need to make sure that we're making the same angle, of course, with respect to some direction. So in this case, it's actually the y component that are going to point, and one is up, one is down. And so my y cancels. And since y cancels, I can say that my net electric field is actually just 2 times one of the x components of the electric field for one of them. And then I just calculate the x component of the electric field. I know that's going to be k q on r squared. And if I'm using angles off of the horizontal, that would be a cosine of theta. And I'm just about done here. I know my value for k is a constant, 8.99 times 10 to the 9. My charge q is the 2 microcoulombs. I'm fine with that. R, I already found at the very beginning, was 5. So I can plug that in for r on the bottom and square it. The only thing that I have left to consider is cosine of theta. And that's actually not immediately evident. I could go and find this actual angle theta using the geography of my 345 triangle. Some of you may actually have the angle theta memorized on a 345 triangle. I do not. But what I would recommend is, since I want to find the value of cosine of theta, I would recommend actually finding the value of cosine using SOHCAHTOA. So cosine of theta, I've already gone here and sort of used the vertical angle rule there. Cosine of theta will be adjacent over the hypotenuse. Okay, so what's adjacent to that angle theta? 4. And then we already know the hypotenuse is 5. So 4 on 5 would be the value of cosine theta. We just go ahead and replace cosine theta with 4 on 5. And then, of course, we'll have a 5 squared in the bottom. Our 2 microcoulombs. Remember, the microcoulombs, this is a mistake that I'm still seeing. The 2 microcoulombs needs to be plugged in as 2 times 10 to the negative 6. 2e minus 6 in your calculator for the charge that will go on top. Okay. People are getting better about that, but I still want to mention that every time. Excuse me. And then you go ahead and plug everything in, and you get the answers 1.2 times 10 to the third. All right. Another problem I wanted to look at from this exam was problem number 5. Yeah, problem number 5 is good because problem number 5 is actually a conceptual problem. So we'll go ahead and call this F5. And we have all these different charge arrangements. And they simply ask us, basically the point here is that you have charges arranged in a square. The only thing that's different is the positive or negative aspect. Sorry about that. So some of them are positive, some of them are negative, and you're simply asked to use your sort of understanding of symmetry with electric fields to determine which one has is it the smallest or the largest? The strongest electric field at the center of its arrangement. Cool. So let's go ahead and draw one of them. I'll start with the number 3. If you're looking at the 777 code. Number 3, we have all positive charges. And we are asked to investigate the electric field at the center, of course, for all of them. With the positive charges, I note the electric field is going to point away from each of them. So that means from this particle, it's going to point down to the right. But from the particle opposite, it's going to point up and to the left. And so those are going to cancel. Same thing could be said for the other pair of particles. The upper right particle is going to have an electric field that points down and to the left. And the lower left particle will have an electric field that points up and to the right. So in this case, since they're all positive, all these electric fields are going to cancel. This arrangement actually has an electric field of 0. Now, the way to proceed through this problem is to take note of all of the arrangements where we have opposite signs then that match, because that's what happened here. Is since this one and this one had the same sign and they were on opposite corners, those electric fields canceled. So which other ones have electric fields that would cancel? Well, arrangement number 4 has a minus across from a minus and a plus across from a plus. So if I'm investigating the electric field at the center, for the 2 negative particles, the electric field is going to point toward. So it'll point toward the upper left particle, and it'll point toward the lower right particle. But again, those are going to cancel, right? So those electric fields cancel. And then just as happened with these 2 particles, the electric fields from these 2 will cancel as well, because they'll both point away and away. And this one will also give us an electric field that's 0. All right, so we're down to 2. It's either number 1 or number 2. And all I need to do is consider which one has cancellation. Problem number 2, or I'm sorry, solution number 2, you have the lower left and the upper right are both positive, so those will both cancel. And so you just have the negative in the upper left and the positive in the lower right that would contribute. But in number one, there are no opposite corners which have the same sign. So there would be no direct cancellation. You could cancel out some components, but you'd end up with only partial components. But maybe it's still worth it talking about the difference between solution 2 and solution 1. So solution 2, we have a negative and we have a positive, and then we have these two positives. And as I just mentioned, because these two positives are on opposite corners, they're both going to cancel. The electric fields are going to cancel, so we can go ahead and ignore them. Instead, what we have is we have the electric field that points due to the negative particle, it points toward the negative particle, and the electric field from the positive particle that also points toward the negative particle. Those will be full value electric fields, whatever the charge happens to be. You have two of them, so the magnitude is going to be 2 times k q over r squared. Now you could plug in an r. We don't know the charge. You could find an r in terms of the side length, but it's going to be the same for all the particles that we consider anyway. So this is good enough for me to compare to solution number 1. So with solution number 1, we have a negative, and then a positive, and a positive. Okay, so from our positives, the electric fields will point away. So from the lower left, it's going to point like that. From the lower right, it's going to point like that. And for our negatives, the same thing is going to happen. So we'll have this and this. So now what we have is, you can sort of see graphically that we have an arrangement here that has twice the pairs that we had on the left-hand side. Doesn't necessarily mean immediately that the electric field would be greater, but since these guys are at an angle to each other and they're not at strictly 180 degrees, they wouldn't cancel out. If you wanted to go one step further, if you're still not convinced, then what you can do is calculate, you can tell that all the x components are going to cancel, and you would instead end up with all of the y components adding up. Now, specifically here, we'd have 4 y components, right? So we'd have 4 times whatever the y component of one of these happens to be. And we can actually say a little bit more about how we'd calculate that. It'll be 4 times k big Q on that r squared. And then since we want a y component, that's going to be either a sine or a cosine of 45. Those are the same. But we can just go ahead and put in sine of 45. And we know sine of 45, if you want to go even one step further, sine of 45 is square root of 2 over 2. And so you could combine that square root of 2 over 2 with the 4 out in front, and that would give you 2 root 2 times kq squared, or sorry, kq over r squared. And so that's an actual comparable solution that you can compare to solution 2 and see for sure that that is the correct answer. Okay, that's several different ways to get there with increasing levels of work, but also kind of increasing levels of certainty as well as we work through that problem. Okay, last one I wanted to do was problem number 3 from this exam, where we are asked to find a force on a particle in a multi-particle system. So yeah, so this is a problem that you've had to do quite a bit of, but that was definitely causing people some trouble in the first quiz. So we have 3 identical charges placed in the xy plane at the origin at 0, negative d, and at negative 2d, 0. Okay, let's go ahead and place them. So we have a particle at the origin. We have a particle at 0, negative d. So that would be down here. And then a particle at negative 2d, 0. So negative 2d would be back here. Okay. And maybe you'd like to label those distances. This is a distance of 2d, and this is a distance of d. Notice I'm not using positive or negative when I'm just talking about a distance. It's an absolute value measurement. And we're asked to find the direction of the force on the charge placed at the origin. Okay, this is a very good one. So first of all, they're all identical. These are all QQQ. They're each Q. And we can go ahead and name these other ones 1 and 2. We're looking at the forces on the particle at the origin. So since they all have the same charge, these forces will be repulsive. So particle 1 is going to push to the right, and we can go ahead and call that F1, and particle 2 is going to push up, and we can go ahead and call that F2. Now, they don't ask me to find the magnitude of the force, which I know is going to be kq over r squared or whatever. And then if I want to find the overall magnitude, I have to do the x squared plus the y squared under a square root. But they actually ask us about the direction. So this is like our hard homework problem that we had to do. We had to find a direction. The equation for the direction of a vector is that tangent of theta is equal to the y over the x. So in this problem, I actually just have one of these forces that is the y and one of them that corresponds to the x. And looking at our picture, it's pretty clear that F2 points directly upward. That's the y direction. So we can go ahead and call y F2. And then we'd have over F1, which is the x, because this force points entirely to the right in the positive x direction. Okay, so we know that this is equal to tangent of theta. Now we do need to do a kqq over r squared, and we need to make sure we use the correct distances. But yeah, we know that this equation will give us a solution. So the left-hand side will just keep at tangent of theta. Eventually we'll have to do an arctan. But for now, let's go ahead and plug in our kqq over r squared. So in both cases, we're going to have kqq. Those q's are going to be the same. So we'll have kq squared for both. And then here we're still doing force F2. We need to do over r squared for that force F2. So what is my r for F2? Well, F2 corresponds to this particle, which is a distance d away from the origin. So we'd have kq squared over d squared. Okay, so that's F2. Now that's all going to be over F1. What are we going to have for F1? It's going to be, again, kq squared on top over the distance. What is our distance for F1? For F1, it's this distance 2d. So I need to have that whole 2d squared, which means that the 2 is also going to square. All right, now I can go ahead and cancel. What's going to cancel here? kq squareds, those will both cancel. My d's will cancel, but make sure I still have a 2 squared on the bottom down here. But the d squared will cancel. So I essentially just have a 1 on the top, and then I have like 1 over 2 squared or 1 over 4 on the bottom, which is actually all equal to just 4. So I have tangent of theta is equal to 4, and then you just have theta is the arctan of 4, which will come out to 76 degrees. All right, it's pretty neat problem, and I like that you're actually using the angle formulation. And this is, again, driving home the way that the vectors work. So hopefully that's a helpful review. Let's see, I had one more written down. Problem number 6. Problem number 6 on spring 21. I'm not going to do, but that's another one for you to try. In that case, we're actually introducing another charge, and we are switching the direction of the force. So I'll go ahead and just write down that if you'd like to work on this some more, take a look at spring number 6.
Are the 21 exams released to us?
Yeah, they're in files. They
They
should be.
are? I thought I only saw 20, up to 20.
Well, that's good to know. I might need to. Huh? They should have warned me, I guess, before I started talking about problems that were on them. I can take a look at student view, I think.
Yeah, I only see up to spring 20.
Well, huh? I wonder.
Unless I'm just blind.
No, I'm sure that you are. It didn't even occur to me to like check if you had those, because they're all in that same place. Huh? Yep. Well, I wonder how much trouble I will be in if I keep going over these. Like, I wonder if they're I obviously don't want to go over them if they are unreleased because they didn't want you to see them, but they also didn't tell us like that you didn't have them. And I just wonder if it's just a matter of them um, forgetting to
Just
make
never
them.
uploading them.
Yeah, exactly.
That seems more likely than they don't want us to see it.
I would think so as well. So okay, so I guess it doesn't help then to tell you to look at spring 2021 problem 6. So I guess I'll go ahead and ask you, are you still able to follow the problems that I'm doing without looking
Yeah,
at the.
yeah. The
Okay, so
problems
this
make
is
sense when you write them out. Yeah.
okay, this is helpful then we'll just keep doing it and
Yeah,
pretend
yeah.
like cool.
These problems seem more in line than like some of the other stuff I've seen on the older exams, if that makes sense.
Okay, great. Then this will be very helpful for people. Okay. Okay, let me pull it back up. All right. So yeah, so I guess it doesn't help to look at problem number 6, but we'll just go ahead and scratch that because I do want to try and, oh no, that's not what I wanted. I do want to get through a little bit more. There's another problem that I wanted to look at was spring problem number 5. Oh yeah. So I guess it doesn't help to put down the numbers anymore, so I won't. But I'll just talk about the problems. Some of these are like really common problems that you've probably seen on a lot of other exams. This is one of them, where you have two balls on strings, and there's an angle theta between them, and they're identical. They give you the mass. They give you a mass explicitly. They don't give you a charge, and they give you the angle as well, and they ask what the magnitude of the charge should be. So let me write down, you're given m and theta, and then they say find the charge of each. So not a whole lot of like information given as far as numbers go. Oh, they also give us the length of the strings as well, which you would need. So let's talk about how to approach this problem. Whenever I see a ball and a string problem, first thing that I do is I think about the forces that are involved. We have, obviously, we're going to have weights. Well, that's probably the less obvious one. The obvious one is that we're going to have some sort of electric force going on, right? Because we're in the electric force problem. The less obvious thing is that both of these are going to have weights because they both have mass. So string a balls on a string problem, that's right what I start to think about immediately. Now you did have a ball on a string problem on the homework, which may or may not be worth looking over. But in that case, it was a ball next to a wall that we're just treating as a sheet of charge that has an electric field that is not dependent on distance, right? We'll get to that in a second. But for this one, the force is going to be between the two objects. So you actually have two objects that are both creating electric forces, and we have to use a different equation. So I start to think when I see this problem, well, what is that electric force? Okay, let's see, I have two identical small spheres. Those kind of sound like point charges, right? So maybe that electric field or that electric force is going to be my KQQ over R squared when I encounter this on an exam.
These are positive, right?
Uh, they don't say, but all of the answer choices are positive. So
Okay.
yeah, they could be negative. So whatever answer you get out could be positive or negative. Right. Okay. And then the other force that we have is a tension. So what we can do is we can go to work on just one of them. So like this is the one that we had on the homework. Let's just go to work on that one because whatever our answer is, it has to work out for both of them. They have to be identical. And so what we had from the homework, if you remember, is we had our tension split up into components, and then we solved and you got tangent of theta is equal to a ratio between the weights and the electric forces. So let's go ahead and run through that solution again. Summing the forces in the x direction, we have our electric force to the right. To the left, we have a component of tension. So we have electric force minus tension times, if I want the x component, that has to be opposite of this angle theta. One other thing, and this is where people this is why this problem is like such a widow maker on the exam, is because in decomposing the tension into its components, we need to use an angle that is off of the vertical, but you'll notice that the theta that they give you is the angle between the two strings. So all of that is to say that the tension, the x component of the tension, has to be sine because it's opposite the angle. And we also need to make sure we do theta over 2 because we only want half of this angle because we want an angle off the vertical. Cool, and then that's equal to 0. And then we sum our forces in the y direction, and we get up, we have the cosine component of the tension. So t cosine theta over 2. And we have minus the weight downward, and that's equal to 0. And then we can solve these equations. We can, add the negative terms over the right-hand side and then divide them. And when you do that, if you do like the division or if you do substitution, whatever, point is to get rid of your tension, you'll end up with tangent of theta over 2 is equal to the electric force over the weight. Just sort of drawing a division there. Okay, so we know theta actually, so we can plug in theta to the left-hand side, and we can sort of consider that to be done. So it's 60 degrees, so you end up with tangent of 30 on the left-hand side. On the right-hand side, I need to do a little bit more work. First thing I need to consider is that the electric force, what kind of electric force do I have here? I essentially have 2-point particles. So that electric force is essentially going to be a kqq over r squared. I know they're identical, so that'll be a kq squared over r squared. And then I'll need to do a little more work on the r. But for right now, we're good. On the bottom, we have the weight. It's just the weight of one of the particles. So that's just 1 mg. So then I take a step back and say, all right, I know theta was given to me, so that's good. I know k is a constant. I know I'm solving for q. On the bottom, I have m, which is given to me, and g is a constant. So the only thing that is outstanding here that we need to deal with is the little r right there. So we can talk about how to do that. R needs to be the distance between, oh no, I'm meant to be in pen mode. There we go. R is meant to be the distance between the two spheres, tiny spheres, small spheres. And it needs to be a dimension, it needs to be a distance. The only distance that I'm given is the length. They tell me that length, and in this specific problem, it was 75 centimeters. It would be something else if you saw this on an exam. But these lengths are both 75 centimeters, and I need to correspond them to this distance r. This angle is 60 degrees, so it's not a right triangle. In fact, though, if I have one angle that's 60 degrees and my sides are the same, what is that, side angle side? That's a 60, 60, 60 triangle, and so r has to be equal to L. Now, all they'd have to do, that happens to be the case for this problem, all they'd have to do is give you that theta is like 55 degrees, and you couldn't do it that way. So just to talk about how to go about it, if it didn't happen to be an equilateral triangle, is that probably what I would do is I would cut it in half and say, I know that this is the length L. I know that this side right here would be half of R. And I know that this angle is half of theta. And then I'd say this is a right triangle. And I can thus say that the sine of theta over 2 is equal to opposite over hypotenuse. Okay, if you did that here, you'd end up getting that r is equal to L as well. If not, you get some ratio of L.
So you would get half the length, right? And then you just multiply by 2 to get the full length there.
Yeah, well, the way I have it set up right here, since I've already called this r over 2,
Oh, okay.
if I literally did sine of theta over 2 is equal to r over 2 over L, then whatever your r that comes out will be the proper r that you're looking for. You can also do, I think, law of cosines. if theta weren't equal to 60. You could do law of cosines with the whole triangle, but I wouldn't be confident enough to do law of cosines on an exam, so. All right, let's see what other ones I wanted to do. Yeah, so one question type that you might see on an exam is that you may not have actually encountered other than in lecture is like the electric field density. So if I were to tell you that there's like these three regions, and in each case I want to accelerate a particle. Let's make this even denser. I want to accelerate a particle from like this point to this point. Okay, I'm going to put a proton in each of these regions, and I should probably have it moving along an electric field line. And I want to accelerate it from the point A to B. The question could ask something like, how much momentum or how much energy or what speed? Essentially, the question will be, in which one of these regions, A, B, or C, will the proton gain the most energy or momentum or speed or something like that? And what it all comes down to is just how dense the electric field lines are. So in region A, where they're all really close together, that tells you graphically, that's telling you that it is a stronger electric field. And so that particle is going to gain more energy, gain more speed, whatever. In B, they're a little more spread apart. That's a weaker electric field. I know that B is weaker than A, so the effect of the electric field is going to be weaker in B than it is in A. In C, where they start close together, but then they diverge, since they diverge on the right-hand side, that means that the electric field is getting weaker as we move from left to right through this diagram. And so that proton will not gain as much speed or energy or whatever as particle A. So again, just the one-shot lesson here is if you see a bunch of electric field lines in a diagram, you look for wherever they're packed in the tightest. That's going to be your strongest electric field, and wherever they're the loosest, that's your weakest electric field. Okay. And spring 2. I think probably do spring 13 maybe. Oh yeah, okay, this is a good one. Okay, this will be our last charge arrangement problem, and then I think we'll move on to some other topics. Okay, so this particular problem, we have two identical point charges. Both have plus q, and they're on the x-axis on the y-axis at plus and minus a. Essentially, it's a dipole setup where you have, except it's not a dipole because they're both positive charges, and they're just located a similar distance a away from the origin. And we're going to take a third charge. We're going to place it at an x-axis at also a, and it's also going to be identically positive. So there's our third charge at a distance a. And they're going to ask us to find the potential energy of the three charge system. Now you could do anything with this, right? We could find the electric field at the origin. We could find the force of on one of these particles, or in this case, we can find the potential energy. So I'm getting a little bit ahead of myself, but I think this is actually the only place where I'm going to touch on potential energy with arrangement problems. So it's a good time to do this. All right, so I know potential energy is going to be K, big Q, little q over R. And I know that I have one term for each pair. So in this case, I have three particles. If I have three particles, that means I have three possible pairs. Now in this case, I have two pairs that are on this diagonal that will be identical. because they're going to have the same distance. What is that distance? Well, since I have an A by A triangle in both cases, this distance is going to be A root 2. And you don't have to be able to get that immediately. You could also just do your Pythagorean theorem if you needed to. So those two green pairs are going to be identical. And then we just have this one other type of pair, which is the two particles that are a distance 2a away from each other. Excuse me, so maybe I'll go ahead and write that this distance is 2a. In both cases, our top is going to be kq squared. So then we just need to add them all up to get our total potential energy. So we have our two that are kq squared over a root 2. And then we have plus just the 1 that is at a distance of 2a. So it'll be kq squared over 2a. All right. Now, the reason why I think this problem is worth taking a second to look at is because this right here is not an answer choice on this particular exam. And so what we need to do is we need to do a little bit of algebra to get these all into the same terms. And so the way that I would do that is I would factor out my common stuff. So in both cases, we have kq squared over a. So in order to get this into a form that matches up with an answer choice, I'd factor out kq squared over a. What would I be left with? For my first term, I have 2 on square root of 2. And in my second term, I just have 1 on 2. All right. And I'm still looking at the answer choice. I'm still saying, I'm not quite there. So what would my next step be? Well, mathematically, I know that I can rationalize my first term there. 2 divided by square root of 2 is the same as just 2, is the same as square root of 2, just square root of 2, right? So I could replace that with square root of 2, and I have plus 1/2. And that doesn't quite match up with either of my terms yet either. But I can compare it to the answer choices here. I have 3 answer choices that are just one single term, kq squared with a 2 on top or bottom and an a. So I can get rid of those terms. And then there's one that has a plus sign and one that has a minus sign. And I'm sort of guessing that's probably going to be the one that has the plus sign. In both cases, though, there's a 2a on the bottom between those two answer choices that have addition in them. So what I would probably try to do next is to factor out a 2. And so when I factor out a 2 here, what I would get instead is I would have kq squared on 2a out in front. And then what would I be left with inside? So it's a 2 on the bottom, actually, I factored out. I would have, this first term would have to become 2 square root of 2, and I'd have plus 1. And that happens to be the answer choice. So I, again, like to talk about this problem because I don't think that the physics is too much difficulty, but do be aware that there is some algebra that needs to be done here. Okay, so this is simply to prepare your brain that you might need to do some algebra to get to the correct answer. And the answers are all given symbolically, so there's no numbers to plug in or anything like that. If you were to, and this is something that I've done before, where I have had this type of problem and couldn't get this algebra to work out on an exam, and my brain was just like not functioning at that level. My brain was on a physics level. And in that case, what I did was, what I have done, I've done this several times, it probably isn't a great practice, but I'll actually make up numbers when I get to like this stage right here and see that my answer choice isn't there. I would make up some numbers for Q and for A, and I would make sure that they're not like 1 or 2, right? You never want to use 1 or 2 as dummy numbers, but you pick like, I don't know, 3 and 5 or something like that. Make sure that they're like mutually prime. And yeah, and then you can plug them in and then plug them into the different answer choices and see which one gives you the same value. Yeah, no problem. And I'll post a recording of this in a little bit once we get off of here. But anyway, yeah, that is a practical like exam taking tip, and something that you can do. You know, it's not guaranteed to get you the right answer, but that would be my recommendation. Okay, so I'm gonna sort of keep going through. As I mentioned, I wanted to spend a little bit more time on those problems than I did in the other topics because those charge arrangement problems seem to be the ones that are giving people the most trouble. But what I'm going to talk about now is we're going to move into Gauss's law. The first thing that I want to go over from Gauss's law is the cube problem. So you had two cube problems on your homework, and you probably come across them on practice exams at this point. So I'm going to go ahead and do another one from a practice exam, and go ahead and pull this guy up. Okay, so print the given formula sheet and bring another handwritten formula sheet. That is my understanding. I my understanding is that you can bring another handwritten formula sheet, and I believe you will have a formula sheet given, but I'm not 100% sure. I'm not sure if somebody else here can verify that. I don't want to give wrong information. Okay, so the specific problem that I'm looking at from an old exam, we've got a cube. I see the cube diagram. Yeah, definitely have both handy. And from what I heard, yeah, you're allowed to bring a handwritten one for sure. So definitely feel free to put down, you know, example problems and stuff on the handwritten one. Um, yeah, that was the word in one of my sections last week. Okay, so this problem, I see the Gaussian cube like diagram immediately in the XYZ plane, and I'm like, all right, sick, this is going to be a cube problem. And then I look at the problem and I see that there's an electric field written out, and I'm like, yes, perfect, I know how to do these cube problems. My electric field is like this. It's like electric field is equal to 5 I hat minus 2 j hat plus 4 z squared minus 3 k hat. And immediately I'm like, good shape. I'm in good shape. Now I know that there's really only 3 different problems that they could ask me to do here. They could ask me to find the flux through a given side, in which case I know that the flux through a side is just plus or minus EA, where specifically I need the electric field that is perpendicular to that side, and it's positive if it exits and it's negative if it enters. I know how to do that. The other thing that they could ask me to do is they could ask me to find the net flux, which is like the capital thing, in which case you just do the sum of all the fluxes through all of the sides. But also, we know that the net flux is that the opposite sides will cancel if the electric field is constant in that direction. So you actually only need to consider the sides that have a variable electric field, which in this case would just be the k hat. And then the last thing they could do is they could ask us to find the charge enclosed, in which case we set this equal to the charge enclosed over epsilon naught. So it's a very limited number of problems they could ask you to do on the cube problem. And in this one that I'm looking at, excuse me, they asked me to find the total charge inside the cube. Sick. So I know what I need to do to find the total charge inside the cube, is I just need to find the flux through each side and add them all up. And I know, since I hat and j hat are constant, I know that there will be a net flux through the opposing sides there of 0. So I only need to find the flux through these sides. And one other little shortcut that I haven't mentioned, but that you can do if you're really comfortable with these, is in looking at the actual construction of this component, notice how there's a variable in one term, the 4z squared, and then there's a constant in the other term. So you can actually furthermore ignore that constant, because that constant will cancel out of both sides. So in doing the flux, I just need to do the flux through, if we're treating, yeah, so this diagram z, the z direction goes up and down. So the flux through the top is just going to be 4 times whatever this z squared is, which is just the side length. So it'll be 3 squared. And then I can neglect that -3 because that will cancel out of the flux in the bottom. And then I just have the area. And the area is just 3 squared. And then my flux through the bottom is 4 times 0 squared times the area, which is 3 squared. And so, of course, this is just going to be equal to 0. And so my total flux then is just this value. And this is a very common thing, especially if your cube has a corner at the origin. If your cube has a corner at the origin, then generally you're just going to have only one side that you actually need to calculate the flux through. And it's usually going to be the side that is located with no part of it touching the origin. So which in this case would be the flux through the top. And so on my net flux will just be equal to the flux through that side that is only due to the variable term. And that makes this a much quicker problem than your Q enclosed is just epsilon naught times that value, whatever that is. Was that 9 squared is 81 times 4 is, oh, I guess I could look at the thing. Nope, because there's an epsilon naught as well. I don't know, 4 times 81, what is that? 162 times 2 is 324. 324 epsilon naught, cool, whatever. All right, so again, you don't have to do all those simplifications that I just did. That is your quickest way to go through the problem. You can also consider the entire electric field component in the k-hat. You can also do the fluxes through the I-hat direction and the j-hat direction if you really want to. But in the interest of time, since we know how to do these, yeah, you can jump all the way to just taking whichever term is variable and finding the flux through the side that is not touching the origin. And that's also a valid way to proceed.
And then the bottom of the cube is at the origin, right? That's why it's 0. And Delaney's like,
Yeah, that's correct. Yeah, and if you did have a homework problem where the like one of the corners is not at the origin, in which case you'd probably have an electric field that doesn't cancel out of the two opposite sides. So yeah, definitely be aware of that. It's very common though on the exam to have the corner at the origin. Cool. All right, so we're gonna move into a different topic here, which is when we have charges distributed. So I think everything that we've done so far has been point charges. And now I'm going to talk about when the charge is distributed through space. So I'm just going to put distributed charge. And essentially what we have is first dichotomy that I want to set is, let me take a sip of this coffee, between integration versus using a standardized equation. So integration versus our standardized equations. The equations, what I mean there is like for point charge is KQQ over R squared, but we also had equations for like a sheet where it's like sigma over 2 epsilon naught, right? Which is like a very straightforward equation to use. But how do I know when I can use those versus when I have to do the integration problems where I have like a rod and I had to integrate over it? Well, the difference is just going to be in a rod problem. So if you come across a rod, there are two different problems that you can do with the rod. This is the only one that you'll have to integrate. You could integrate a sheet, but they're not going to ask you to do that in this class. They'll ask you to do that in higher level physics. You could integrate with some sphere stuff, but again, that's a higher level physics question. So the only thing that we need to do in this class that we need to be responsible for is for the rod problems. And the difference between an integration rod problem and an equation rod problem just comes down to whether it's finite or infinite. So if it is finite, we have to integrate. If it's infinite, then we just use the equation, and this equation, which I'll go over again in a second, but this equation is just lambda over 2 pi epsilon naught r. And so that's if your rod is infinite. If you have an infinitely charged rod, it's going to have a linear charge density of lambda, and your electric field is just going to point radially outward from it, and that electric field is going to vary with distance r from the rod. And that's it. So that's actually better. It's better when it's infinite. It's more painful when it's finite. And when it's finite, this is when you need to proceed with the integration. So let's go ahead and talk about a finite rod problem. So in order to do the finite rod problem, we have to solve two integrals. We have an x and a y integral. So the x component of the electric field is equal to k dq over r squared times This maybe isn't always the case, but I tend to stick to cosine of theta. Some people switch them around, but for me, I just use cosine of theta for x, and then for dE sub y, it'll be the same thing, k dq on r squared times sine of theta. Now, typically, when we're doing these problems, we can use symmetry, and the symmetry will allow us to immediately tell that one of them is equal to 0. So symmetry means that we only need to solve one. And I can talk a little bit about at least the symmetry and the setup in just a second. And then the steps for actually solving, the first step is to set dq over dl equal to q over l. And the point of this is to replace dq replace dq with a differential of space. What do I mean by that? I mean, basically, I want to turn dq into a dx or a dy or a dz or a d theta or maybe even a dr. But I want to take a differential charge dq and I want to replace it with some variable of space. Once I do that and I know which variable of space I'm replacing it with, then step 2 is to replace all variables in the problem with that spatial variable. Replace all variables with this guy right here or constants. Okay, so this is sort of like kind of a rough overview guide, but hopefully we've seen this before and this is jogging a memory rather than covering new territory here. Well, let's go ahead and take a look at an example. And I'm going to do the one, we did 2 on the homework and review those for the exam. I'm going to do the one that I haven't done, which is we have a rod on the x-axis and we're looking at a point P. And I'm actually going to take this a step further too. So let's see, the rod is going to be length L, and it's sitting on the x-axis, and the point P is a distance D away from the end of the rod. And what I'm going to do here is, when we did these problems on the homework, we had a constant charge. So that was what allowed us to do dq over dl is equal to q over l. What I'm going to do in this problem is I'm going to do something that I have seen on old exams. It was old exam where the average was very, very low. I think this semester when this showed up was maybe 2014 or I don't remember. It's been a very long time. But it was an average of like an 8 out of 20 on this exam. And what they did was instead of having a constant charge density, they give you a lambda of x that is like what would be the easiest way to do this? I think you'd have like, hold on, I got to make sure I get my units right. Do I want it to just vary with x? Sure. Let's just do a constant times x. It could be they could give you any function, right? But it would have to be a function of x because the rod lays on the x-axis. So anyway, this is the setup, right? And we're asked to find the electric field at the point P, and maybe they tell us that A is positive, and we just need to find the electric field. Okay, so I know that my electric field at the point P is going to be, I'm just going to move that P down. I know that that electric field will point to the right. So this is the sort of step 0. Remember step 0 I said is that usually we only need to do one of our 2 integrals because usually one of them is automatically equal to 0 just by looking at the problem. Well, in this case, I know that this electric field is pointing entirely to the right because the point P is entirely to the right of the rod. And so what that lets me do is that lets me say right off the bat that the E sub y is equal to 0. And so I just need to solve my E sub x integral. Okay, so let's go ahead and write down the E sub x integral. We have d E sub x is equal to k dq over r squared. And then we have cosine of theta. But what is the cosine of theta here? If my point P is on the x-axis, it's actually cosine of 0, which is equal to 1. So the cosine of theta here, it actually doesn't introduce any difficulty to this problem, because we have a constant cosine of theta, just because the charge, again, is located all on the x-axis, and my point P is also on the x-axis. Okay, so great. So next step is we know we want to replace dq. And as I said on the last page, usually, like on the homework problems, we have dq over dl is equal to q over l. Now this q over l is the definition of the charge density, lambda. So in this case, we actually cannot say that it's equal to q over l, because that represents a uniform charge density. Here, our charge density is not uniform, it varies with x. So we actually have to set this equal to our lambda of x, which is equal to a times x. Now you may think that this makes the problem more difficult, but it actually makes it a little bit easier for us, because we're basically explicitly being told here what we want our differential distance variable to be, right? So we know that we want to take this dl and we want to turn it into a dx or a d theta or d whatever. Well, in this case, we are explicitly being told to turn that into a dx, because we have a lambda of x that is in terms of x. So that tells us that dq then is going to be replaced with ax dx. Great. And then the last thing is to that will allow us to replace dq. And then our last step is to replace all other variables with either our variable of space or to replace it with a constant. So the only other variable that we have here is r, and r is also something to do with x. So to take a little piece of the rod, say we have this little piece, I know that this right here is that distance r that I want to plug in. And I know that this distance over here is x. So how do I turn r into x graphically? I know I'm going to need to relate it to the other lengths here. I have this length, big L, and I also have this length d from the end of the rod to the point P. How do I express r in terms of all of this? Well, r would be big L plus that distance d, and then I want to subtract out the contribution of x. So again, that's that little r is equal to d plus L, which is the total distance from the origin out to my point P, is d plus L, and then I subtract off the distance x. And so now why would I do it this way? Well, because again, my job here was to turn that r variable into my variable of integration, which is x, and some constants. And I have accomplished my goal here. I'm doing wonderfully. And then I can go ahead and do these two substitutions into my equation. And I now have that dE sub x is equal to k. My dq is being replaced with ax dx. And then cosine of 0, I already said, goes to 1. So we're good with that. And then the bottom, we just have d plus L minus x squared.
In the top right of your screen, is that E of x is equal to 0 or like E of 2?
That's E sub y. The y component is equal to 0.
Okay. So is this for a finite rod where we have
Yes.
variable? Okay. So this
Yeah,
is
if
a
you had,
finite with variable charge or density, I mean.
yes, yeah, that's exactly it. So it's a finite rod. It only goes from 0 out to L. That's the rod right there. So it's a finite length of the rod, and it has a variable charge density, which is, this may not be a problem that you've seen before.
Okay.
But
Now,
yeah,
if we had an infinite rod with a variable charge density, it wouldn't really appear, right? Because that's just because it's infinite. It's
that
too
would
hard to
be
like.
super gnarly.
Yeah, because they'd have to because it goes on forever, right? So they probably would give you a finite one. They're going to give you variable charge.
Yeah, so I think the best way to answer that is to say that our last step here is to integrate this. I'm not going to do this integral because I actually, if you had an integral that's difficult, I think they'd have to give you like they have to give you the solution to the integral. But the important thing is that the limits of this integral go from 0 to L because that's where the rod is. If you were to have something similar where it's an infinite, you would just integrate from like negative infinity to positive infinity. So you'd also have to have an integral that works out that way. I haven't seen that, but I guess the answer is that you could, in fact, do it if it did come up. But I have seen this problem, and I think on the where this problem did come up in a previous exam, I think they gave a general solution to this integral on the formula sheet, or they maybe had a different lambda of x. So I'm kind of pulling this from a very far back in my brain. They might have had a different lambda of x that allowed us to cancel stuff out. Like I could say that lambda of x is equal to d plus l minus x squared or something, so it cancels. Okay, cool. I am sort of satisfied with where that's at though. And gonna go ahead and move on to the other, oh, I shouldn't have maybe deleted it. But the other, yeah, so I said that for an infinite rod, right? For an infinite rod, we can just use an equation. So here's our equations for like constant charge distributions where we don't have to integrate. The only integration problem you have is for a finite rod. For everything else, here's your list of equations. So we have a point charge, which we've already talked about. A point charge has an electric field of K big Q over R squared. And then we also have the rod, which we've already talked about, and that has an electric field of lambda over 2 pi epsilon naught R. And you'll see this on your formula sheet, I believe, as 2k lambda over R. It's the same thing. They just replaced 1 over 2 pi epsilon naught with 2k. And then we have our two different sheets. We have a conducting sheet and we have an insulating sheet. Again, conducting sheet versus insulating sheet. For a conducting sheet, your electric field is sigma over epsilon naught. And for an insulating or non-conducting sheet, your electric field is sigma over 2 epsilon naught. Just make sure you have in big letters the difference between those two. And remember, when you come across a sheet, your very first question is this conducting or is it insulating or non-conducting? And I would write that very big at the top of your paper before you go to work on the problem that has a sheet in it. Okay. So we'll take a look at a couple of problems having to do with this in a second. But I also want to talk about the conducting spheres. So in both cases, we are inside, conducting versus insulating spheres. In both cases, we're inside. When we're inside a conducting sphere, and this one is important enough to go here and to be on your formula sheet. If you're inside a conducting sphere, the electric field inside of there is always 0. This seems like it's not really an equation, but it's such an important, I think, fundamental way that the electric fields manifest inside of conductors that you should have that written down somewhere. And then for inside an insulating or non-conducting sphere, for this one, the electric field is K big Q little r on big R cubed. And I'm going to make one note here. This assumes uniform charge density. If, it's a big if because I'm not even sure if I've ever seen it in this class specifically. If you don't have uniform charge density, then you have to actually do an integral. And you have to do an integral kind of like the rod problem, and it's very annoying to do. And if you have a non-conducting sphere with a non-uniform charge density, I would recommend not spending a lot of time on that problem and doing the problems that you can get the answers for. I could talk about it at the end. I can come back to this if you'd like, but I'm actually not going to spend too much time talking about when it's non-uniform. but it would actually work kind of like um, the problems that we just did this past week with resistor, where you have a charge density, a current density, and you integrate over the circle to get the current density. But instead of integrating over a circle, you're going to integrate over little differential surface areas. So your dV is equal to 4 pi r squared dr. But again, I can't really recall ever seeing that, but I just want to mention that as a caveat. Okay, I do want to do a couple of problems here. Problem number, well, doesn't matter, I guess. But one of the problems here, we have 3 parallel sheets. They're all insulating. So first thing I write down on my paper is that they are insulating sheets. And I maybe even go ahead and write down the equation from the formula sheet that says E is equal to sigma over 2 epsilon naught. And I'm given the charge densities of 1 and 2. And then they ask me to find a charge density on 3 that makes the electric field 0 in one of my given regions. So here's my sheets, 1, 2, and 3. And they tell me that 1 has a positive 2 charge density, 2 has negative 4 first charge density, and 3 we don't know. And they want me to make the electric field 0 in the region between sheets 1 and 2. So they want us to have an electric field of 0 in here. So first thing I would do is label the directions for the electric fields for sheets 1 and 2. Remember, the rule with sheets, since there's no distance variable in this equation, the rule is that really the only thing you ever have to be concerned with is the direction. So the electric field is going to point away from positive and toward negative. So sheet 1 is positive, so the electric field is going to point away from sheet 1. That'll be electric field 1. Sheet 2 is negative, so it's going to point toward sheet 2. That's electric field 2. Since they point in the same direction, they will in fact add together. And since this electric field equation is just equal to sigma over constants, you could just add the absolute values of these sigmas together to get the sigma for sheet 3. Now, one thing that I know for sure is that the electric field needs to point in the other direction from sheet 3. If E1 and E2 are pointing to the right, E3 has to point to the left. And since it's pointing away, that thus means that sigma 3 is positive. And then since it just needs to counteract both of these in the same direction, it's just going to be positive absolute value of 2 plus absolute value of negative 4, which is just 6. And then you have, of course, some units. But that's a very quick way to get through the sheet problems. I happen to think the sheet problems are pretty straightforward and good problems to tackle. I do have one that is maybe a little more difficult. I'm not even going to spend time on it. There's one with 4 sheets.
There's a problem just like this on one of the practice exams, except that both charges are negative. So, and it also asks you to find the electric field to be 0 and the region halfway between. So since they're both pulling against each other, it's different, right?
Yeah, so let's talk about that. So all that does is it reverses the direction for E1, right? So now E1 is pointing toward sheet 1, so it's going to point to the left if I make sheet 1 negative. In this case, yeah, so in this case you have E2 is going to have a magnitude of 4 over the constant stuff, and E1 is going to have a magnitude of 2 over the constant stuff. So the net there is, again, just 4 minus 2, but we still know that E2 is bigger, so E3 still has to point to the left to cancel out the net effect from 1 and 2. The only difference is that it's now, rather than being absolute value of negative 4 plus absolute value of 2, it's absolute value of negative 4 minus absolute value of 2. And so you end up getting 2 for your sigma 3. So it is the directions. You do have to keep the directions straight. And keep in mind that whenever this is a fundamental rule of dealing with vectors, is that once we assign a direction on a diagram like this, then when we go to do the actual calculation, we always use an absolute value. So it might be worth maybe putting absolute values on your formula sheet where you have the electric field for the sheets.
Would it be easier to just like think about it as in you need, since it has to be 0 in the middle, you just have to find a value for 3 that creates a value at 2 that's equal to the value at 1, if that makes sense. That's a lot of words. Like, because we know that
Uh,
we have four is applying on 2, and 2 is applying on 1, but if we want a value of 0 in between, we need -2 to be the value on 4, so 3's got to be +2 to cancel that out.
Wait, so okay, let's use different numbers because we happen to have some symmetry here. Let's use a
Okay.
let's make sheet 2 a -5. So now what
Yeah.
would be the
So it'd be 3, right?
yeah, exactly, exactly.
Okay, so I was making sure I could think about it in like I guess an easier, less mathematical way of just canceling out to make 1 and 2 equal, quote unquote, so that the place in between is 0.
Sure. Yeah, yeah, yeah. So you could think of E3 adding together with E1 to cancel out E2. Yeah, I like that. That's a way that I think about these problems too. All right. Um, yeah, one that I just want to mention also is that on this exam that I happen to be looking at, they had the rod problem from your homework where you have the two different rods. There's like the inner rod and then there's the shell, and they have the graph and you have to read the graph. Literally the exact same problem from the homework. So that it is something that happens every few semesters where that problem shows up. So take a look at that problem if you'd like to review the rod problem. Other than that, yeah, if you have an infinite rod, you just use the equation. And then, okay, and then I had some sphere problems I wanted to do. One of these problems is you have a non-conducting sphere that has a charge big Q, and then they put a point charge little q at the center of this non-conducting sphere. And they give you that little q is equal to -1/2 of big Q. And they ask at what radius of magnitude the electric field is equal to 0. Okay, so very good question here. And what we know is that we'd have two electric fields at whatever that radius is. So it's going to be somewhere, some little r distance to the edge of the sphere. And at that location, our net field is just going to be equal to the field from big Q plus the field from little q. And we want them to be equal to 0. And from big Q is an insulating sphere. So I know from my formula sheet, I know the equation for an insulating sphere that is uniformly charged. I know that it's K, big Q, little r on big R cubed. And then little q is a point charge. So remember, a point charge is just KQ over R squared. So it'll just be K, little q over little r squared. This is all equal to 0. The last thing that I would do here is replace little q with -1/2 big Q. And I could also cancel out a couple things at least. I could cancel out my k's here. So my first term is q times little r over big R cubed. And then I have -1/2 big Q on little r squared. And this is equal to 0. And then I just go ahead and solve from here. And I will end up with, once my little q's cancel, I'm going to do a little bit of algebra here in my head. Don't worry too much about wasting brain power doing algebra right now. But you'll end up with,
We're solving for little r, right?
yeah, little r is
Okay.
equal to big R on the cube root of 2 is what you'd end up with here. And then you'd plug in 1 on cube root of 2 in your calculator and get 0.79. So luckily, you can give your answer as a decimal here. Cool. Yes, big R is a radius of circle, and they tell us that explicitly in the problem. Sorry, I didn't write that down immediately, but yeah, big R is the radius of the entire sphere. Cool. Okay. Oh yeah, one other problem that I want to mention. I'm not actually going to look at one explicitly. I'm sure you've seen it as you've gone through. The one where you have the 3 charges that you connect with wires. So you have or it's actually 3 spheres, and you go through the series of operations, and you either connect them or you ground one of them. And so just remember that when you connect two spheres together, you average the charges, and when you ground them, the charge goes to zero. This is a problem. It was a homework problem, and I just mentioned that it's just like there's just like a specific procedure for doing this one problem, but this one problem loves to show up in exams. So I just wanted to make mention of that to look at that homework problem. If you haven't, I think it's actually in like the very first homework assignment, and I think it's chapter 21 because it's actually an electric force problem. Um, okay, I'm going to move into this next topic, and the next topic is the relationship between potential and field. So we have the two different definitions that are sort of the inverse of one another. We have that the potential difference is equal to the negative integral of E dotted with ds. Remember that the way that this usually manifests is either the negative integral of a one-dimensional electric field like E sub x dx, or it's the negative of the area. This would be the area of, and I think this is where people ran into difficulty on the quiz, delta V is the negative of the area of an E versus X or Y or Z graph. So it's the area of the electric field graph that gives you delta V. The flip side of this equation is the electric field is the opposite of the derivative of the potential with respect to an X or a Y or a Z. And what this tells you is that the electric field is the opposite of the slope, but it's telling you explicitly that that is the slope of the V versus X or what? Excuse me, X or Y or Z graph. So the potential versus the potential graph, in other words. So on the quiz, there is a potential graph that looks like it was set up for areas. And so a lot of people immediately were like, I'm going to find the area under this triangle. And that is not actually what you're asked to do, because you're asked to find the electric field of that potential graph. So you just needed to find the slope through one specific region of that graph, wherever the x value is that they told you, which was like x equals 2.67. If you happen to get that problem, then you know the one that I'm talking about. So let's take a look at some exam problems. First one, right off the bat, touches on this exact topic. Here's what the graph looks like. And the electric field goes like this, and then it goes like this. And the specific values that they give you, like this value right here corresponds to x equals 2. This one corresponds to x equals 4. And then over here we have an x equals 5. And they tell you that this is, let me write this down, that this is an x versus an e sub x graph. So they also give you a couple values for e sub x. They tell you that up here e sub x is equal to 4. And they tell you that down here e sub x is equal to 2. All right, and they tell me that the potential at x equals 0 is set to be equal to 0. So that's V naught is equal to 0. And they ask us to find the potential at x equals 5. So what is V at 5? All right. I need to find a potential from an electric field graph. Potential from the electric field graph, that's this guy right here, the left-hand side. So I need to find the negative area of that electric field graph. So my delta V is equal to the negative area. My delta V will be V final minus V initial, which will just be whatever that V is at 5 that I'm looking for. And thus I just need to find the total area. And keep in mind that I will have positive area on top, negative area in the bottom. This chunk right here would be equal to 8. This chunk will be equal to 1/2 base times height will be 4. And this chunk down here will be 1/2 base times height. This will be -1. All right, so adding all of that up, I have 8 plus 4 is 12, minus 1 is 11. And then I also have a negative out in front. It'll be a negative 11 volts. All right, I'm gonna pause the recording real quick and take a little break. I don't know how long we've been going. Was it 11:45? Was that when I started? Oh, I guess we started a little closer to. Yeah. Okay. So it's about. Let's take a little bit of a break. I'll come back in like 5 minutes. Um, but yeah, I'm gonna grab some coffee and stretch my legs just a second. Okay. Um, cool. So, see, we just did that one. Another pretty good one. And there's another one on the same exam. Oh, yeah, okay. Yeah, no problem. So I got another problem here that gives me a potential. And it's tells you the potential is, they actually say like in words, which is strange, but it says the potential is described by the following functions. 1 on XYZ. And they ask us to find the magnitude of the electric field at a point P of 1, 2, 3. All right, so this is a very good problem for multiple reasons. One is that it seems pretty purely and theoretical, but it also forces us to work in the X, Y, and Z. And I know I need to find the electric field from the potential. So I go back here and I say, okay, I'm trying to find the electric field given the potential. Well, I know the potential is I know if I find the slope of the potential graph, I know how to do that. I can find the slope of the potential graph, but here they're giving us a function for the potential. So I actually have to use this definition up here, that the, say, x component of the electric field is a negative derivative of the potential with respect to x, but also the y component of the electric field is a derivative with respect to y, and the z component is a derivative with respect to z. So I have to do each of those. So my E sub x is the negative dv dx. And what is the derivative of 1 over x? That's x to the negative 1. So you multiply by the power and then decrease the power by 1. So you end up with x to the negative 2 there. So it would essentially just cancel out my negative sign out in front. And I have 1 on x squared yz. And that's going to give me one component. And I can go ahead and plug in 1, 2, and 3. But they actually ask for the overall magnitude. So I also need the y component, which is the negative curly v curly y, which is 1 on, it's going to be a very similar integral, or derivative, where you'd have negative 1 on x y squared z, but then there's another negative out in front that cancels that out. So it's x y squared z. And then you could probably guess where this is going for the z component. We could probably follow this pattern and say that we end up with 1 on x y z squared. All right, and then the next step is to plug in our values for x, y, and z. So our first one, we'd have 1 on 1 squared times 2 times 3. For our second one, we have 1 on 1 times 2 squared times 3. And then for the last one, we have 1 on 1 times 2 times 3 squared. All right, each of these will give us a different value. The first one is 1 on 6. The second one is 1 on 12. And the third one is 1 on 18. And then since I'm asked to find the magnitude of the electric field, I need to do this one squared plus this one squared plus this one squared and put it under a square root. And you happen to get 0.19. You can do it in your calculator. But yeah, this is very good. I would consider this to be kind of a higher level problem, but I like that it is actually doable if you can do the partial differentiation.
They haven't really talked about partial differentiation that much. It's just like the main application of it.
Yeah, this is it. So uh, all the partial derivative tells you is that you treat whichever variables you're not integrating
Yeah,
with
yeah,
respect to.
I know how to do it, but like
Yeah,
they
yeah.
just haven't really talked about it in physics. Like we've been learning it in calc, but
Oh, gotcha. Okay, yeah, yeah. So, this is the only case where I've ever seen that you had to actually use the knowledge of like treating the other ones as constants. So, that's really all I did right here, for instance, was just left y and z right where they were, like they're constants, and just differentiated with respect to x. Cool. All right, got some other problems to deal with this. Okay, got a problem here. An electric field E, they're giving me the electric field in vector notation. So I have an I hat and a J hat, but they're both constant. They give me a potential at one of my points. All right. So my electric field is 4 I hat minus 5 J hat. And they tell me the potential at the point the point 4 comma 5 is, oops, sorry, it's supposed to be a 5. I stopped looking at my screen when I was writing that. Is it 4 I hat minus 5 J hat? Okay. So my potential at the point 45 is 25 volts. E magnitude would be the sum of the square rooted. Yes, yeah, exactly, exactly. So yeah, it's just square root of a vector. All right, so here's my electric field, here's my potential at one point, and then they ask, what is the change in the electric potential energy of a proton as it moves from 4,5 to 3,2? So they want to know what's the change in potential energy in moving from 4,5 to 3,2. Okay, so this problem has a lot going on. The first thing that I noticed is that I'm asked to find a change in potential energy. I have long since closed that very first slide that I made, which was poor planning on my part. But I know that there's a way to relate the change in potential energy to the change in potential. It's just like the force is equal to Q times E. We have one that says that delta U is equal to Q times delta V. So, in order to find the change in the potential for the proton, well, I know the proton's charge. I just need to find my delta V. So that's going to be my potential at 3 comma 2 compared to my potential at 4 comma 5. Now, how do I get my potential at 3 comma 2 from the electric field? Well, how do I get potential from electric field? To go back here, how do I get potential from electric field? That's got to be this guy right here, right? The potential difference comes from something about doing the integral of E with respect to distance or something like that. All right, and I know that this is the electric field, so I would like to somehow put all this together and say that delta V is going to be equal to the negative integral of E with respect to the differential line segment ds, path length. And I only need to find delta V itself. So on the right-hand side, I can say that this integral of E dotted with ds would be, since it's a dot product formulation, this would be the opposite of E sub x dx plus E sub y dy. But we could also go a step further here and say, well, these are both integrals, right? But in both these cases, we have constant electric fields. So what happens to an integral of a constant? If I want to do the integral of dx, what is the integral of dx? That's just going to be x. So when I integrate e sub x as a constant with respect to dx, that's just e sub x times x. In other words, I can simplify this to just being e sub x times delta x, however far I'm moving, plus e sub y times delta y, as long as I consider the relative directions between the motion and the places that I'm going. Maybe a better way of putting this then, to make sure that we don't disrespect the dot product needing to have a certain direction, is that we do have dot products in here. Oops. And we need to make sure that we take note if our electric field is pointing in the same direction that we're moving or the opposite direction. So for our x component points in the positive x direction. I'm moving from 4 to 3. I'm moving in the negative x direction. So I have a positive component for the electric field, a negative component for my motion, and so that's going to give me a negative dot product because those are in the opposite directions, and it's negative 4 times 1 because I'm moving just 1 unit in the x direction. And I have plus in the y direction, I have a negative 5 for the electric field, and I'm moving from 5 to 2. So I'm also moving in the negative direction as well. So that's going to be positive for both of them. So I'd have positive 5 and positive 3. Okay, there's some other ways to go about this to make sure that you get the signs correct. The signs are important here. So feel free to ask if you have more questions about how to exactly get the sign. But once we do this, we end up with, let's see, negative 4 plus 15 is 11. And there's a negative sign out in front. So that negative 11 is my delta V. And I actually don't even need to know the potential at the 0.45 because I'm just looking for the change in the potential and thus the change in the potential energy from this equation.
So when we're looking at this, right, we're finding the change in V. So we're not even fully using that delta U equation. We're actually just solving for it using the integration.
Well, ultimately, what this problem is asking you for, this problem is asking you for delta U. So
Then you just multiply that by Q.
yeah, so you multiply negative 11 by the charge of the proton. That was the last step, yeah.
Okay, so you split it up into E of X and E of Y. I don't totally get the signs. So from 4 to 3 and 5 to 2, we're both going in the negative direction for both of those, right?
Yes.
So I get the negative 4 and then the change of 1. But then why is it positive 5?
So we're going from 4 comma 5 to 3 comma 2, right? Okay.
Yeah.
So, and we're moving through a region, so we're going like this. We're moving through a region where the electric field is positive in the x component and negative in the y component.
Okay,
So
so it's based off the I and the J there.
yes, yeah. So we have a positive x electric field and a negative y electric field. So my motion, I can treat it as moving through the y and the x. And if I do it this way, you'll see that your y motion points in the same direction as your y
Yeah,
field.
so it cancels out because we have the negative. Okay.
Yeah,
So
yeah. So
okay, so
since
that's
go
just
ahead.
based off the E field. That's just based off the E field. So since we have the negative 5 on the Y field and we're going in the negative direction, it's a positive, quote unquote.
Yeah, it's a positive dot product because remember your dot product is A dot B is equal to the magnitude of A, magnitude of
Times
B
the magnitude of B
times the
and
cosine
then
of theta.
cosine. Yeah, okay.
So it's
This
like
is the
cosine of
cosine
0
is
or cosine of
0.
180.
Yeah.
Right. So this one is a cosine of 0, but since my x component of the field points to the right and I'm moving to the left in the x direction, that one has cosine of 180, which is a negative dot product.
I got you.
Cool. All right. Um, okay. So last thing I want to talk about is circuits. And I think what I'm just going to sort of go over is just at least the equations and then maybe a couple circuit problems themselves. But first thing I want to do, I guess, is talk about the different types of circuits. Or I'm sorry, the different components. So capacitors and resistors, those are our two components, right? So here's your equations, just to make sure you have these and know how to use these at the very least. So for capacitors, we have a parallel plate capacitor. We have a spherical capacitor. And then we also have an isolated sphere. And each one of these has a different equation. The capacitance of a parallel plate capacitor is epsilon naught A over D, where A is the surface, or is the area of the plate, and D is the separation between the two plates. For the spherical capacitor, this is where you have two different spherical shells that are concentric. Capacitance is 4 pi epsilon naught AB over B minus A. So your two different spheres here are separated by some distance B minus A, because the radii of each are A and B. And usually you just treat A as the smaller radius, B as the larger radius. If you happen to switch them, you'll get a negative capacitance, which doesn't mean anything physically, so you won't get any problems wrong that way, because capacitance is always positive. And then, okay, but this is different. So where you have two spherical shells like we do here, is different than the isolated sphere, the last one down here. The isolated sphere is just a single, it could be solid sphere, it could be a shell, whatever, but it's just sitting in space. This is the Mercury problem from the homework. And this is just 4 pi epsilon naught times big R. And yeah, and if you can find the capacitance, then you'll sometimes just be asked to do a simple calculation with the capacitance and with the equation that the voltage of the capacitor, so maybe we should put delta V for voltage, is equal to the charge on the capacitor over the capacitance. So that equation kind of goes hand in hand. Of course, we're going to use that when we talk about circuits in just a second as well. The other component that we have in circuits is resistors. And you just have one type of resistor that we are responsible for in this class, which is that the resistance is equal to rho, the resistivity, times L over A. So rho is a resistivity. It is simply a material fact of whatever metal the resistor is made out of. L is the length. As your resistor gets longer, think of it as a longer hallway that you have to pass through. If you have to pass through a longer hallway, you're going to face more resistance from people walking the other way. And then area is the cross-sectional area of the resistor. So if the hallway is wider, then you're less likely to like bump into people as you're passing down the hallway. Okay. So let's go ahead and take a look at some problem. Oh, one other thing that I wanted to mention, I guess, is the dielectric. So yeah, let's just do one quick page on dielectrics. Dielectric will come into play for capacitors. And the way it manifests are in three different equations. So we have that the capacitance is equal to kappa times epsilon naught A over D, where kappa is a dielectric constant. You could also, if you needed to find the electric field inside of a capacitor, you could just do kappa times EA is equal to the charge enclosed over epsilon naught. Excuse me. And then the one other equation is that the charge induced on the dielectric itself is equal to the charge times 1 minus 1 over kappa. Okay, this is just a homework problem, and this is just charge induced. And let's see, I'm looking at one right here where we have an air-filled capacitor has a certain capacitance. We triple the plate separation and add a dielectric, and they give us a new capacitance. They ask what the dielectric constant is. So let's do that problem real quick. Okay, so we have an initial capacitance that is equal to 3 picofarads. And we know that this would be equal to an epsilon naught A over D. And then we're also given a final capacitance that's equal to 6 picofarads. And in this case, we have placed a dielectric in there, and we've also tripled the plate separation. So the dielectric is kappa. We don't know what it is. We like to solve for it. And then we have epsilon naught. We tripled the plate separation. So we actually didn't impact A on the top, but we triple the separation on the bottom. So that's 3D on the bottom. Okay, so now I have these two equations. Ultimately, I'd like to solve for kappa. And it's up to you how you're going to solve for this here. I'd probably isolate, here I have epsilon naught A over D. I know that that's going to be equal to 3 picofarads. So I could make a substitution for all of this epsilon naught A over D in this equation right here. And so I'd have 6 picofarads is equal to kappa over 3 is the only stuff that remains over here, times 3 picofarads when I do that substitution. Don't have to do it this way, but this is probably your quickest way. And then, picofarads cancels out of both sides. We have a 3 that cancels out of top and bottom, and that'll give you a kappa that's equal to 6. There are other ways to solve through the problem as well. You could set up a ratio, you could divide one by the other and then cancel some stuff out. But ultimately, those are the types of problems that you need to do. So what are we doing really here is we're doing an SAT problem where the basic equation that we're using is the parallel plate capacitor equation with the dielectric. Keep in mind that the kappa for air is 1. So we've used that kind of implicitly in our initial definition here, but that's something just to be aware of. And let's see, let's do at least one capacitor circuit problem. All right, so I'm going to copy down this diagram. We have a voltage source, and we have one capacitor, two capacitors, three capacitors, and there's going to be a lower branch. So we have 2 on this lower branch. And they have different capacitances. They're all in terms of the C. So this one is C, this one is C. The one in the middle here is 3C. And then we have a 2C and a 2C. Cool. And they connect this to a battery potential difference V. They ask, what is the charge on the 3C capacitor? They don't give us any values here. They just ask us for the charge on this one right here. And so we're going to give our answer. If you were looking at the exam, remember it's multiple choice. The answers are all given in terms of CV. So we need to give our answer in terms of CV as well. And so as we work through this capacitor, we're going to want to, keep our C in check. And I am going to need to sum up the capacitor initially and find the equivalent capacitance. So there's a quiz problem where it actually wasn't to your benefit to find the equivalent capacitance, and those who did, I think, had more difficulty on that quiz problem. But on an exam, most likely your place to start is to find the equivalent capacitance initially. So what are our rules for capacitors? If you forget it, remember that the voltages add together when you're in series. So, and I know that my V1 plus V2, whenever I'm in series, that's my rule. I know I have the same charge. So this is the same as charge over C1 plus charge over C2. And this is how I know that the equivalent capacitance for series is the inverse one, the 1 over C1 plus 1 over C2. Of course, you can just put those rules right in your formula sheet if you'd like, and you won't ever have to come up with that. But if you're ever on a desert island, that's how you can derive the relationships. So in series, it's the 1 over C. In parallel, it's a direct addition. So these two are one. Oh no. Like that back, please. These two are 1 over 2C plus 1 over 2C, which is 2 over 2C, which is 1 over C, and then you invert that, and you'll get a C. So combined, those two give you a capacitance of C. Next up is I know that these capacitors are in parallel with my 3C up above because they're connected on both plates, so 3C. And so I have C plus 3C, which will give me one 4C capacitor. And then the last thing is I'd like to sum them up to the last two capacitors. You'll notice that these are all in series now. So again, we have to do the inverse. 1 over C plus 1 over C plus 1 over 4C, which is 4 over 4C, 8 over 4C, 9 over 4C, so 4C over 9. 4C over 9. If you didn't follow me on the math, don't worry about hurting your brain with math right now. You'll do plenty of math when you go take the exam. Okay, so that is my equivalent capacitance. Once I have my equivalent capacitance, I know that the voltage of the battery is equal to the total charge times, or rather divided by the equivalent capacitance. And this, I can rearrange this then to find my total charge. It's the voltage of the battery, which we're allowed to just say is V times the equivalent capacitance, which is 4C on 9. All right, so 4/9 VC. Remember, my answer choices are all in terms of VC anyway. So I'm going to keep VC in the game here as I'm working. Now this is the total charge. That means that anything that is connected in series to the battery will have this charge. So this capacitor will have 4/9 VC. This capacitor will have 4/9 VC. Okay, I don't care about those. Most importantly, this 4C equivalent capacitor that I had, this whole thing will have a charge of 4/9 VC. So I can then calculate the voltage. The charge is going to be 4/9 VC. So that's my Q. And then I have over the equivalent capacitance, which was 4C. So this gives me 1/9 V. Now this is the voltage on this 4C equivalent capacitor. I have the 2C branch that I don't care about, but I do know that that's connected in parallel to the 3C that I do care about. And since they're in parallel, that means that they're going to have the same voltage. So this voltage is the voltage over the 3C, and thus I can find the charge on the 3C capacitor, and that'll be equal to the voltage, which is 1/9 V, times the capacitance, which is 3C, and that gives me 1/3 VC. Okay, so that's a very representative type of problem, and that was maybe about 8 minutes. I guess I was talking a little bit. Maybe about 8 minutes, as long as you know what you're doing, you know which direction you need to go. These are very doable problems, and yeah, so definitely make sure you do a few of those in prep and know how to work down the circuit. In other words, know how to sum up the circuit to get the equivalent capacitance in the one direction, and then know how to break the circuit back up using your parallel and series rules for charge versus voltage being shared over series and parallel respectively. All right, I think I want to do a little bit more. I think the last thing I want to talk about is I'd like to do a resistor problem. One homework problem to look at is the one where you have the reverse polarity. We have like a positive negative connected to a negative positive, and you had to subtract the charges. Just make sure to look over that one. Maybe even put it on your formula sheet that you're taking in. And okay, so I want to talk about, let's see, power first of all with resistors. I don't actually think I'm going to do a problem with power, but the power of a resistor is equal to I squared R. Other equations that are useful, you can also say it's equal to IV, and it's also equal to V squared over R. And you use this equation oftentimes in tangent with, or in, I don't think that's the right use of the word tangent, but you usually use it along with the voltage of the resistor, which is equal to I times R. And as I already covered, the resistance of a resistor is rho L over A. That's if you're actually given the material of the resistor and need to do something with it. And okay, so one problem that I want to do here is they tell you A resistor has a resistance of R. And we're going to take this resistor and we're going to stretch as a wire. We're going to stretch it so that it becomes 10% longer. So stretch it so that our final length is 10% longer than our initial length. So that would be 1.1 times your initial length. We'll go ahead and call this resistance R naught. And then they also say we want to maintain the volume. So our final volume is equal to our initial volume. And they ask what the new resistance is going to be. So, okay. So what are we going to do here? How are we going to relate length and volume and all this stuff? How are we going to relate this all to all this stuff? Well, it's going to be right here, right? So length and volume, whatever, has to somehow be packed into this equation. And I'm going to clear off the left-hand side. But we're just going to use that resistance equation. And then we're actually, it's again kind of a SAT type of problem. So resistance initial is equal to rho times length initial over area initial. And resistance final is equal to rho times length final over area final. What I would like to do is get my resistance final in terms of resistance initial by replacing the variables on the right-hand side with the same variables up here. So which one can I replace right away? I can actually replace the length on top. And so that would give me, if I just go ahead and plug that in, I'd have rho times 1.1 length initial over area final. And then I need to somehow replace the area final with some initial area. So where's that going to come from? Well, probably something to do with the volume. And specifically, if you look at the way that we define our area, remember our area is a cross-sectional area. So we have like a wire that's something like this. The wire has some length L out to some distance. And then the cross-sectional area here is the thing that is the area. Well, a definition of a prism and the way that we calculate the volume of a prism is that it's just the length of the face, the area of the face multiplied by the length of the object. So volume can always just generally be written as area times length. And so in this case, where I'd like to work on this equality, I could replace volume final and volume initial with area final and area final, length final, and set that equal to area initial, length initial. I do not know my any of these values, but I do have a relative relationship between the two lengths. So I can go ahead and make that substitution as well. And I'll have 1.1 area final times length initial now is equal to area initial, length initial. And now I'm kind of cooking. I know I can get rid of my L initial. Last thing is, keep in mind what I want to substitute out. I want to substitute out area final for something in terms of area initial. So I need to rearrange just a little bit here to get that my area final is equal to area initial divided by 1.1. Now I have something that can be substituted. I can go ahead and perform that substitution. And I'm getting a little running out of room. Let me give just a little bit more room. When I do that substitution now, I'll have that this is rho times 1.1 L naught over, on the bottom I have A naught over 1.1. Last thing is, what did I ultimately want to do is I want to get some number times this, because that will be the same as having some number times the initial resistance. And so I have a 1.1 that needs to be factored out, and then I have a 1.1 all the way in the bottom, on the bottom of the bottom, the denominator of the denominator. So ultimately that will come back up, and we'll end up with a 1.1 squared times rho L naught over A naught. And so my answer for this problem is, again, because they're just asking for a ratio, the answer for the ratio is that it's just this guy right here, 1.1 squared, which is whatever that happens to be, it's going to be bigger than 1.1, right? 1.21 because it's 11 times 11. Haha. Great. All right. I think that does it then. I think we've done quite a bit here. If you have any questions, I'll go ahead and take them. And if not, I'm going to hop off and post this recording.